So we're on chapter 6.6, rational equations and problem solving. So the first thing we're going to do is we're going to solve rational expressions or rational equations because we're solving for a specified variable. So pretty much these are the steps we're going to take. They're really natural steps. We're going to clear the denominators by multiplying both sides by the Lcd of the denominators, just like we did in section 6.4 and 6.5. We'll use the distributive property when necessary to do that. Then we're going to combine like terms. Terms with the variable that we want to solve for go on one side. Terms with the other variables go on the other. Then we solve for the variable. So here we have our first one. And this is really, I think, one of the most important skills that you will use in life. Many times you might look up and find a formula for something that you need, but the formula has more than one variable, and the variable that you need is not the lone variable on one side of the equation. So what you do is you solve for the variable that you need. In this case, we want to solve for x. So I just wrote x in yellow just to remind us that's going to be the variable that we solve for. So our first step is we're going to find the LCD of x, y, and z. Now all three of these are prime in the sense that they're polynomials that cannot be factored. So the LCD is just their product. So we multiply both sides by the LCD. And this is what you need to get in the practice of doing. Even when one side of the equation is a single term, go ahead and enclose it in parentheses. So here I'm multiplying both sides. If I didn't multiply both sides, I'd break the inequality. And here again, all we're doing on the left-hand side is distribution. So x times y times z times 1 divided by x is the same as x times y times z divided by x. So the x's cancel out, and that gives me y and z. The same over here, x times z divided by y. The y cancels out, and it leaves me x and z. And on the right-hand side, the z's cancel to leave me x and y. So make sure you feel comfortable with how I got to here. So always, when we clear the denominators, and we do it by multiplying both sides by the LCD, we get an equation that has no fractions. Here you have to resist the step, some of you might have it, to simplify the left-hand side by pulling out the z, because z is a common factor. But here we want to take note that we want to solve for x. So the second step is to isolate the variable terms, or the terms with our variable on one side. So here I have an x and a y. So that is a variable term. It has an x in it. So I'm going to take the xy here on the left-hand side and move it across the equal sign, and it becomes positive. And my y and z are going to stay by themselves. So now if you'll note, I'm solving for x. If you want, you can use different colors. If you need that help, that's fine. So you treat everything else just like, it doesn't look good, just like they were variables. So my next step is going to be to factor out my x values here, my x terms. So xy divided by x leaves y, minus xz divided by x leaves me z. And my right-hand term is the same. Now again, here we're solving for x. So what we need to do is to isolate x, I have to get rid of the y minus z term. And we do so by just simply dividing both sides by y minus z. You just pretend like that's a constant. You don't know what it is, and it's really not, but you just pretend it is. And when I divide both sides by my y minus z, notice what happens. The y minus z terms cancel on the right-hand side, and all I have left is yz divided by y minus z, and that is equal to x. Is one last habit you should put provided y minus z is not equal to 0, because that would result in division by 0. So this formula is valid provided y minus z is not equal to 0. And I really can't tell you if the homework requires that or not. In grad school and even in advanced undergraduate classes, we got hit on the head by failure to take note of this right here when the denominator has variable terms or a variable in it, would always get points deduced. So it's become such a habit from being a math major, math grad student, that I just do it automatically. And I think you should too. But clearly if my math lab is not enforcing it, you won't, but keep in mind. So here's our next one. If a certain number is subtracted from the numerator and added to the denominator of 9 divided by 19, the new fraction is equal to 1/3. So we're going to let x be the certain number. It's our unknown. And that's what they're asking us to find. Find that number. So we have 9 divided by 19. And it says, so 9 is the numerator, 19 is the denominator. If the certain number, which is x, is subtracted from the numerator, that means it's subtracted from the numerator. It's in the top. It's above the division line. And it's added to the denominator. The resulting value is equal to 1/3. So we need to find the LCD of our denominators. Notice that 19 plus x is prime, and so is 3. So the LCD of two prime numbers are just their product. I'm going to write them as 3 times 19 plus x. So that's my LCD. So let's do our multiplication. Both sides. And we're going to cancel the terms that we can cancel. Here we have 19 plus x in the numerator, 19 plus x in the denominator. That's all that can be canceled. Over here I have 3 in the numerator and 3 in the denominator. Remember, the result is always going to be an expression with two polynomials. Polynomial on one side equal to a polynomial on the other. And at this point it's really elementary to solve, and I invite you to pause right now and solve it. But again, we're going to just use distribution. So 3 times 9 is 27. 3 times minus x is minus 3x. And this is equal to 19 plus x. So solving this type of equation goes all the way back to what we did at the very beginning of this course. So that's going to give me 29 minus 19 is equal to minus plus 3x plus x. The minus became the plus when I moved it over. So 29 minus 19. Oh, that's not 29. Did I say 27 and write 29? It's Monday. It doesn't really matter that you make a mistake, as all humans do. The point is that you catch it at some place. So over here, 3x plus x is 4x. And we don't really need that plus right there. You can just put it over there to again emphasize the minus 3x becomes a plus. And 27 minus 27 minus 19 is 8. So now I just divide both sides by 4. And the result is 8 divided by 4 is 2, and that's equal to x. We're not quite done yet, because I've reserved for the last step here what we were doing at the very first step in, I think it was 6.4. We gotta make sure that we list all values of x that have to be excluded. So that means we set any variable term in any of the denominators equal to 0. So if the denominator has a variable in it, you set it equal to 0. There's no reason to set 3 equals to 0, because it's never going to be equal to 0. And that gives us that minus 19 is equal to x. And this is the value that x cannot be. So we just recall, this is what the value of x that results in division by 0. But we didn't get that. We got x is equal to 2. So that's an acceptable solution, and indeed it is. I'm going to go ahead and do this right now since we have time. So we had, what was it, 9 minus x over 19 plus x. And that's supposed to be equal to 1/3. So we discovered that x was equal to 2. So let's just check. So 9 minus 2 over 19 plus 2. Well, 9 minus 2 is 7, and 19 plus 2 is 21. And 7 divided by 21 is the same as 1/3, and that checks. So if you have time, you can always check. So let's do example number 3. So this is really very, very close to what we just did. The only difference, again, our number, x will be our unknown number, unknown value. The only difference is that if we read this, what we do is we add x to the numerator and we subtract it from the denominator, and the result is 5/2. Well, again, we need to find the LCD of 11 minus x, which is prime, a prime polynomial, and 2, which is also prime. It's the least of the prime numbers, the very first one. So since these are both prime, the LCD is just equal to the product. So we're going to multiply both sides by the LCD. And it's really simple. 2, 11 minus x. 2 times 11 minus x. So here, let's cancel out our terms. If you need to, you could put parentheses down here. If it helps you see that the 11 minus x and the 11 minus x cancels. On this side, the 2 and the 2 cancel. So what do I have left? 2 is still there, just the 11 minus x canceled. So I have 2 times 3 plus x. 3 plus x must be put in parentheses because it's 2 times the numerator. So you have to multiply the entire numerator by 2. And that's equal to 5 times 11 minus x. And again, it's really pretty elementary at this point. 2 times 3 is 6. 2 times x is 2x. 5 times 11 is 55. And 5 times x is minus 5x. So what I like to do is I like to move variables so that my variable terms are positive. So that means I need to move the minus 5x to the left-hand side to get 5x. It's going to be joined with my 2x, which requires that I move my 6 to the other side, and it becomes negative. So 5x plus 2x is 7x, and 55 minus 6 is 49. Now all we do is divide both sides by 7, and I get my answer that x is equal to 7. But we still need to remember to make sure that's an okay value. So we go back up and we take a quick look, and we said 11 minus x, it's my only denominator that has a variable in it, equal to 0, and we get x is equal to minus 11, and that's the one value that has to be excluded if it were to occur. But I didn't get that value. I got x is equal to 7, so that checks out. So these are a new type of problem, and has to do with problems relating to proportion. So let me give you a quick definition. So proportions, or problems related to proportions, they're mathematical statements. That means they assert something is true or false. A mathematical statement that asserts two ratios are equal. So equations involving or modeled by proportions, that's what they do. So I needed to define something else for you, I believe. What is a ratio? Well, a ratio is just another word for a rational expression. So clearly 3/5 is a ratio, and 5x plus 1 over 2x minus 3 is another ratio. So basically we're going to be dealing with ratios. There's one other thing that's kind of unique about ratios. When we're talking about things that are enumerated, in this case houses, then the things that are enumerated sometimes are different. But with ratios, the things that are enumerated, which are many times called units, are the same. In other words, as we'll see in the next example, I think the very next one, you have ratios where the units aren't the same, and instead of calling those ratios, we call them rates. So let's just look at this. In the USA, 7 out of 20 homes. So let's look at how to translate this. In, out of D translates to N divided by D. So D is your total number. And in this case, N is the portion of the total under consideration. And that's what a ratio is. So here in the USA, 7 out of 20 homes built since 1990 are heated by electricity. So we have 7 out of 20 that are heated by electricity. So we have 20 total homes, and out of those 20, on average, 7 of them are heated by electricity. So if this is our rate, how many homes in a community of 36,000 built since 1990 would you predict are heated by electricity? So our new total of homes is 36,000. And we want to know what portion of those, that's my X value, are heated by electricity. Now, the 1990 and the 1990, you can just ignore that. And they have to be the same number for this particular type of a problem. So basically, we just modeled this problem into an equation where X is the number of homes out of 36,000. Is that right? Yeah, 36,000. What is special about that portion? Heated by electricity. This type of problem is extremely common. And I'll be honest with you, when I learned how to do these in algebra way back in high school, that's when I started doing really well in math. So here we're going to solve it. We're going to solve for X. So to solve for X, we multiply both sides by 36,000. So notice on my right-hand side, the 36,000s, they cancel. And over here I have 7 times 36,000 divided by 20 is equal to X. Now that's not very informative. That's exactly what X is equal to, but we have to simplify it. And we're going to simplify it by first dividing 36,000 by 20 and then multiplying by 7. So let's divide 36,000 divided by 20. Well, a good old trick that we know is when we're dividing two numbers and they both end in 0, you can just cross out those zeros. You can cancel out those zeros. Pretty much what I'm doing is I'm dividing the numerator by 10 and the denominator by 10. So this is equivalent to dividing 3,600 by 2. And if you're good at doing things in your head mathematically, this is the same as 36 divided by 2, which is 18 with 2 zeros. So it's 1,800. But I want to find the total, so that means 7 times 36,000 divided by 20 is the same as 7 times 1,800. And that's the same as 7 times 18 and tack on 2 zeros. And 7 times 18 is 126. and I tack on 2 zeros, and I put the comma where it is. So that's equal to x. So 12,000, I'll write it a little bit better here. 12,600 homes would be the number of homes out of 36,000 heated by electricity, if that ratio holds. Okay. All of these are pretty straightforward except the last one. The last one, we'll take some time explaining it, and it's really not as bad as it seems. So here, this is a typo I've never fixed. Let's just read the problem. So Melissa Scarlatti can clean the house in 4 hours, whereas her husband, which should be Jack rather than Sack, can do the same job in 5 hours. They've agreed to clean together so that they can finish in time to watch a movie that starts in 2 hours. How long will it take them to clean the house together? And can they finish before the movie starts? So if the final number of hours is greater than 2, then they can't finish before the movie starts. But if it's less than or equal to 2, then we can say they can finish before the movie starts. It doesn't really matter whether you go, if it's less than 2 or greater than or equal to 2, it doesn't really matter there. So this particular type of a problem is a work rate problem. So just like ratio, we have a new term, which is a rate. So pretty much a rate is a ratio where the units in the numerator are different than those in the denominator. And remember, unit is just a measure, is just a word that says or tells you the thing being measured. So here is the paradigm example. You'll never forget it. We all know a rate of travel, or what is more commonly known as a rate of speed. And that is miles for us in the United States per hour. So here we have a fraction. The thing being measured in the numerator are miles, and the thing being measured in the denominator is time. And that's another general expression for something that is more abstract about speed. What we really have, miles, is a particular measurement of distance. And hours is a specific measurement of time. Because if I talk about solar system times or galaxy times, light years, how far something can travel in 1 year. 1 light year, which is a measure of distance over the time 1 year. What about the speed of sound? That might be miles per second or kilometers per second. So miles per hour is what happens to be measured when we're in our cars in the United States. But speed in and of itself should be thought of as distance over time. And we'll use that in the next problem. In this particular problem, the rate that we're talking about is the number of houses cleaned That doesn't look right to me. Houses cleaned per hour. And this is typical of a rate, especially a rate involving time. How many screws can a machine shop make per hour? How many ball bearings can SKF manufacture per day? So that's typical of rates. And what we're going to have here is we're going to have one rate added, which I'm going to call rate sub 1, plus another rate added, which is rate sub 2. And when I add two rates, you always get another rate, which is a rate sub 3. So what are those rates? So it's Melissa's rates. The rate Melissa cleans her house is going to be added to the rate that Jack cleans their house. And together we're going to get the rate that both clean a single house in 1 hour. So now we just have to plug and chug. What is the rate that Melissa cleans? Melissa cleans one house in 4 hours. Well, Jack is not quite as good as she, and he cleans one house in 5 hours. So if they work together, how long will it take them? So X is a time variable. And where is our time variable? How long will it take them to clean one house? So it's one house, and X is our time variable. So all I have to do is solve this. So the LCD of 4 and 5 and X is equal to 20X. 5, all of these are prime except 4. So, but the prime factors of 4 are 2 and 2, and neither of those factors are included in 5. So if you did the table, you would find, well, here we have 2 and a 5 and an X, 4, 5 and an X. Not very good at freehanding lines here, but there's 2 factors, 0, 0, 0, 1, 0, 0, 0, 1. So it's 2 squared times 5 times X. That's 4 times 5. That's 20 times X. So let's go ahead and let's multiply both sides by 20X. So again, remember that the end result of this is going to be an equation without fractions. That's the beauty of it. So 20 times 20X times 1/4 is 20X divided by 4, which is 5X. 20X times 1/5 is the same as 20X divided by X. 20X divided by 5, which is 4X. And here you can see the X's cancel out, and I got 20. So 5X plus 4X is 9X, and that's equal to 20. So X is equal to 20 divided by 9. So that's what my X equals. That's how long. That's hours. So there's two ways. We want to know, is X greater than 2, or is X less than or equal to 2? Well, one easy way to do this is to turn this from an improper fraction to a mixed fraction, So when I turn 20 divided by 9, well, 9 divided by 20 will go 2 times with the remainder 2. So it's 2 and 2/9. So 2 and 2/9 is definitely greater than 2. So the answer is they will not finish in time. Unless, of course, they start earlier. As a matter of fact, they would miss 2/9 of an hour. If their television show started right on the dot, they would miss 2/9 of an hour, probably half of which would be commercials. So now let's do the very last one. So I'm going to let you read that really, really fast. And this one is a little bit involved, but it's not as bad as you think. So Stephen, he's in some kind of boat, takes 1.5 times as long to go 72 miles upstream in his boat as he does to return back to where he started from. If the boat cruises at 30 miles per hour in still water, so that's just the speed of the boat, what is the speed of the current? So let's put some things together. So this is kind of the puzzle. We've been given a puzzle, kind of like a jigsaw puzzle. So we're going to take the stuff given us and let's put them together. So the first thing we're going to do is we're going to declare what x is equal to. Well, it tells us we're asking for the speed of the current. So x is the speed of the current. So here, we kind of draw a little picture. So here's our river. So Steve starts in a boat, and my drawing is really pathetic. And we're going to say that the river, it's flowing this direction. So he starts going upstream. He goes 72 miles. And then he turns around and he goes downstream another 72 miles. So let's think of something. When he's going upstream, so let's record this down. So upstream speed. Well, that's going to be equal to the boat speed. When we talk about boat speed, we're always talking about speed in still water. That's just kind of assumed background knowledge. Boat speed in still water, but he's going against the current. So that's minus the current speed. For those of you who can't swim, if you've ever been like in an airport or you're going to Universal Studios and also Disney World, you have those people movers. So if you get on the people mover and you go and you walk on the people mover, so your speed is sped up. It's the speed of your walking plus the speed of the people mover. If you get on it going it the other way, then whatever speed you're going forward is pushed back by the speed against you. So the upstream boat speed is boat speed in still water minus current speed. But when you go downstream, you're getting a boost. It's your boat speed, which I'm just going to call your boat speed. It's understood to be in still water. You're going to get the boost plus the current speed. So as always, we're going to make a table using all of this information. So the table is going to be pretty elementary. It's just going to have a place for upstream and then downstream. And then we're going to divide it, and remember our speed is equal to distance over time. So we want to put all of those over here. Our distance and then our speed and then our time. Now, as it turns out, the distance going both ways is exactly the same. It's 72 miles. And the speed is the boat speed, which is 30 miles per hour. I'm getting it from right here. So the upstream distance and the downstream distance are the same. Speed upstream is the boat speed in Stillwater, which is 30 miles per hour, minus our current speed. Our downstream speed is 30 miles per hour plus my current speed. Now here I need to use my formula given by here to fill in this. So I need to solve this for time. So I'm going to let, sometimes, many times, instead of speed, S, they'll use R for rate. But I'm going to go ahead and use S for speed. S is equal to D divided by T. We need to solve for T. So that means T times S. I just multiply both sides by T is equal to D. And then I divide both sides for S to get T is equal to D divided by S. So my time here is my distance, which is 72 divided by my speed, which is 30 minus x. And down here, this is 72 divided by 30 plus x. But if we go back to the original problem, we know we're not quite ready to solve it, because I've not used this factor of 1 and 1/2 times is long to go 72 miles. So we have two travel times. So time upstream and then time downstream. Now, which of the two are greater? Well, it takes more time to go upstream, right? It takes more time to go upstream than it does downstream. But I need this converted to an equality. So what I need to do is go back up here, and it says Stephen takes 1 1/2 times as long to go upstream as he does to go downstream. So if I multiply 1 1/2, which I'm going to convert to 3/2 in improper fraction, if I multiply 3/2 times the upstream, then this is still greater than the downstream. So in order to make this inequality, I have to make or increase the value of the time downstream. So we do that by multiplying that by a factor of 3/2. If you try to translate this directly, just using the words instead of thinking about it conceptually, in the way I just told you, you will attach the 3/2 to the time upstream, and you'll get a nonsensical answer. The answer you get will be either negative or something will be wrong. I think what happens is it becomes negative. So now I've converted I've got an equality. Notice I didn't have an equation until I did this. I had things in a table, but no equation. But now I have an equation. So my time upstream, which is 72 divided by 30 minus x, is equal to 3/2 times my time downstream, which is 72 over 30 plus x. So let's find my LCD. My LCD of 30 minus x, that's prime. It's a prime polynomial. 2 is prime. 30 plus x, also prime. So the LCD is just their product. 2 times 30 minus x times 30 plus x. So that's what I'm going to multiply both sides by. I knew I had to do something up there. So again, 2 times 30 minus x So now let's just go ahead and let's cancel out. So here I have a 30 plus x and a 30 plus x. I have a 2 in the numerator, a 2 in the denominator. Over here I have a 30 minus x in the numerator and a 30 minus x in the denominator. So what I have is 2, that remains, times 30 plus x, that remains, times 72. And over here I have a 3, it remains, the 72 remains. Remember, I cleared the denominator, so you don't have to worry about the fractional part, and then a 30 minus x. Now let's solve this the best way possible. Both sides contain a factor of 32. So I'm going to use the principle of equality by dividing both sides by 72. That's completely legal. So that allows me to cancel out the factors of 72 on each side, and that gives me a much easier equation. 2 times 30 plus x is equal to 3 times 30 minus x. So 2 times 30, 2 times x, 3 times 30, 3 times x. Again, I want my x values to be positive, just preference, it doesn't really matter. So minus 3x is going to come over and become 3x, and it's going to join my 2x value. And then my 60 is going to move on the other side and become minus 60. So that gives me 5x is equal to 30. So x is equal to 30 divided by 5. So x is equal to 6. Is 6 an okay value? Well, 30 minus x is equal to 0. That implies x is equal to minus 30. Or 30 plus x is equal to 0. Implies x is equal to, that's supposed to be a plus there, x is equal to minus 30. And 6 is neither of those values. This is a perfectly acceptable answer, and indeed the correct one. If you had attached to the 2/3 to the wrong side, you would have a weird answer here. You would have x is equal to minus 6. But that actually tells you something. It tells you that you've reversed the direction from your model of the current. But that's another time and another day and another class.